Everyone, welcome to another lesson of physics. Today we will be talking about inclined planes. And these are forces as an object goes down a slope. So, an inclined plane is like what's pictured right here. And this is a tool that's used to move objects from one height to another. So essentially just a ramp or a hill. Now this allows for the movement of an object without lifting it directly against gravity. So it makes it a little bit easier to move something from point A to point B. Like a wheelchair ramp helps someone get up a little bit easier compared to the stairs. Now, some common inclined planes. These are some that we can see in everyday situations, such as a car parked on a hill. We can take a look at a roller coaster car climbing up the roller coaster. And also movers pushing a piano. Makes it a little bit easier than just lifting up the piano. The inclined plane makes it a little bit easier. Now let's take a look at some of the calculations, because we are always interested in physics with quantifying how much these forces are. So forces on an incline is going to be a little bit different than how we've done forces before on a flat horizontal surface, because we can no longer use x and y because everything is at an angle. So instead, we're going to take a look at this in terms of perpendicular to the surface and parallel to the surface. So perpendicular being out of the surface and into the surface. So the first force that we're going to have is the force of gravity onto the plane. So the force of gravity is going to be broken into two components, the perpendicular component and the parallel component. And we're going to be able to calculate this using Fg perpendicular equals Fg cosine theta. And the normal force is also in this direction and is opposite the perpendicular component of gravity. So if there's no other forces in that direction, they will be equal and balanced. Next, we have the parallel direction, and this includes our force of gravity along the plane, which we will use Fg parallel equals Fg sine theta. And we also have the force of friction that opposes it. And this can depend on many things, the normal force, the coefficient of friction, just like we've done before. Now I want to take a look at the force of gravity as this inclined plane has its angle increased. So this green arrow represents the force of gravity down, and this is going to remain constant as it's done in many other problems. But watch what happens as we increase the angle of the plane. You'll notice that the perpendicular component starts long and the parallel component starts shorter. And we'll see that this perpendicular component continues to get shorter as the parallel component continues to get longer. And eventually, if we get high enough up, the object will slide down due to having the very large parallel component. Now let's take a look at some of the general trends. So what happens to the component of weight that points into the plane as the angle is increased? So we're going to see that this decreases. So our Fg perpendicular continued to decrease as we increased the angle. Now what happens to the component of weight that points along the plane as the angle is increased? So we saw that this Fg parallel continued to increase along with the angle. Next, let's take a look at what happens to the normal force as the angle is increased. And we see that this is going to decrease because the normal force depends on Fg perpendicular, which is also decreasing. Now what happens to the friction force as the angle is increased? So we'll see that the frictional force will also decrease because it depends on the normal force, which also decreases depending on the perpendicular component of gravity. All right, so now let's take a look at an example. So in this example, we have a 50 Newton block sliding down a ramp inclined at 30 degrees. It wants to know what is the magnitude of the normal force. So in order to find the normal force, the first thing we want to do is draw out our picture, like I've done below, where you can see the 30 degrees, and we have the block on there. I also drew on the free body diagram, but it's kind of hard to work on when it's at an angle. So what we're going to do is rotate it. So we're going to have our normal force up, our force of gravity perpendicular down,
force of friction to the right, and our parallel component of our gravitational force to the left. So now in this picture, the block's not going to be flying off the ramp. So our normal force and our perpendicular component of our gravitational force are going to be equal to each other. And we said before that the perpendicular component of our gravitational force is going to be Fg cosine theta. And we can plug in our values. So it tells us it's a 50 Newton block, so we know that's going to be our gravitational force times cosine 30. So now we want to take our calculator and plug this number in and see what we get. All right, so we get that our normal force will be equal to 43.3 newtons. Okay, so now we want to know what is the magnitude of the weight down the hill. So this is referring to what our parallel component of our force of gravity is equal to. And as discussed before, this is going to be equal to Fg sine theta. So from here, we can plug in our Fg, 50 newtons. And this time, it's going to be sine 30, which will give us that the parallel component of our force of gravity will be equal to 25 newtons. Now, if the box is sliding with a constant velocity, what is the magnitude of the friction force? So if there's a constant velocity, that's saying that our net force is equal to 0. And in our x direction, there's only the parallel gravitational force and the frictional force. So they're going to have to be equal to each other. So if they're equal to each other, then we know that our force of friction will just be 25 newtons. Now we can determine the mu k between the block and the ramp, our coefficient of kinetic friction. So we're going to use our friction formula for our kinetic friction equal to Fn, and we're solving for mu k, so we'll get it by itself, force of friction on top, and normal force on the bottom. So now we can plug in our values. For our force of friction is 25 newtons. This is over 43.3 newtons. So when we plug this into our calculator, we will get that this is equal to 0.577 for our coefficient of kinetic friction. And as a reminder, there are no units for our coefficient of kinetic friction since it's just a proportion. Okay, let's take a look at another example. So now we have a 2,000 Newton car that rolls down a ramp inclined at 65 degrees. So it asks, what is the magnitude of the normal force? So we have this diagram drawn out again. In this case, it's rolling, so we're going to assume no friction unless it tells us otherwise. So we have the free body diagram drawn out already. And we can say that the component down is this Fg perpendicular, and to the left is this Fg parallel. Then upwards, we have our normal force. So again, we'll see that our normal force is just going to be equal to our Fg perpendicular. Our Fg perpendicular is equal to Fg cosine theta. We can plug in our values again. So this is 2,000 newtons this time, and cosine 65. So when we plug this into our calculator, we'll find that we get 845 newtons, roughly. Okay, so now, what is the magnitude of the weight down the hill? So just like before, when it says the weight down the hill, this is talking about our Fg parallel, because this is what's pointing down the hill. It's going to be equal to Fg sine theta. And we can plug in our values again. So Fg is 2,000 newtons and sine 65. So now when we plug this in, we will find that the component pointing down is going to be 1,813 newtons. So we can see that the force of gravity is pointing more down the hill, so it's going to have a greater influence in that direction. Now, if the car rolls with no friction, we want to determine the acceleration that the car experiences. So the acceleration that the car is going to experience is going to be all in the x direction because the y direction cancels out. So we're going to do the sum of the forces in our x direction. It's going to be our net force. Now there's only one force in this direction, which is Fg parallel. So we can find that our net force is going to be equal to 1,813 newtons. Now we can use our net force formula, F net equals ma, to find our acceleration. So a equals F net over m. And we can plug in our values. So our net force is 1,813 newtons, but we don't have the mass yet. We're actually given its weight before, so we're going to have to solve for what our mass is. So we can do this using the formula Fg equals mg. And in this case, we know our gravitational force, and we know g. So we can get m by itself. Let's do Fg over g. M equals 2,000 newtons divided by 9.81 meters per second squared. So from that, we will find that our mass will be roughly equal to 220 kilograms. We can plug that into our formula, and we will find that our acceleration for this car is going to be 8.24 meters per second squared. So maybe they'll think twice before forgetting to put on their parking brake. All right, so now how far does the car roll in 3 seconds if it started from rest? So our time is going to be equal to 3 seconds. Our acceleration is equal to 8.24 meters per second squared. And it's starting from rest. So our initial velocity is going to be equal to 0 meters per second. It's looking for how far it rolled. So we're looking for d. So now we're going to use our kinematic formula that has d and t. So it's going to be d equals VIT plus 1/2 AT squared. Now we said VI is equal to 0, so this component will cancel out. So we get D equals 1/2. We'll plug in our A, 8.24 meters per second squared, times our time, which is 3 seconds squared. And when we plug this all into our calculator, we will find that it is equal to 37.1 meters. All right, so that's going to be it for this lesson. I hope you all have a great rest of your day.